All right, so for today's lecture, we're going to talk through some advanced SQL techniques. These build upon some of the SQL queries we've already looked at this semester to try to get some other kinds of information out of some of our relational databases. And one of the big ideas for today's SQL queries is the idea of joins. A join is where we take two or more tables that have something in common with them, and they're all part of the same common domain, and we combine some or all of two or more tables into a single table or view. And for the most part today, we're talking about views, where we're temporarily looking at data that is blended from two or more locations, and we're showing it on the screen, and then we would use it to inform a real world business decision if necessary. So we're going to be looking at a couple different types of joins. An inner join is where the joining condition is based upon some equality between different values in common columns. So you might want to think about things like primary key, foreign key, right? Those two things have to be equal to one another. If they're equal to one another, we can match between one table and another table. We've been using that as sort of our common language to get a relational database to work. That really lends itself to these join queries. So we're going to take advantage of those relationships to ask some interesting questions about our data that's being stored in all these different tables. So as an example, we can play around with a database that would look something like this, where we've got our customers, our orders, our products, and our order lines. In this particular example, the customer ID is a primary key in the customer table, but it's a foreign key in the order table. So I can look up information in the order table, and anything that says customer ID, I could go get the rest of the information about that customer in the customer table, in this case, the customer name. Or in the other direction, if I was in the order line, there's a relationship between the product table and the order line table. And so anytime I have a specific product that's being ordered in an order line, in an order, I can look up more information about that product using that foreign key, primary key relationship. So we're going to do that using queries. And here's one way that we could potentially do this is for each customer who's placed an order, what's the customer's name and order number? Well, this is a relationship between the order table and the customer table. It's only customers that have placed orders. We could have customers that exist in the customer table that aren't in the order table. We can't really have an order that doesn't have a customer though. So it's every customer that is in the order table. I want to know that customer's name and order number. And I'm going to share my screen slightly differently so that I can even show you what this looks like, how this demonstrates. If I were going to paste this into SQL, I could take this thing and try it out. So let's try it in SQL and then talk about what this actually does. So I'm choosing my select statement, the customer ID from the customer table, the last name and the first name and the order ID from both my customer table and my orders table. So in this case, you can see I do customers.customer ID. This very well could also be orders.customer ID because they exist in both places. And that is actually the field that I'm going to be connecting between the two of them. So I could choose one or the other, but you have to specify. So the one I'm going to display is the customer ID that's coming from the customer table. And then the last name and the first name, well, they happen to come from the customer table. The order ID happens to come from the order table. And I'm joining these things where the customer ID in the customers table equals the customer ID in the orders table, the primary key, foreign key relationship. And so what we see are only customers that actually have orders, and we can see the specific order IDs that show up. And that does mean that some of these customers might show up more than once because they placed more than one order. So for every order where we have a matching customer, we show that customer's information. And you can imagine this is a really useful way of querying the data to get information that is relevant across these multiple tables. There are multiple ways to write these queries. In many cases, you're going to see the use of aliases to further clarify what's actually happening here. So you can see that in this case, it says c.customer ID instead of the customer table.customer ID. And what they've done here is they've given customers an alias C, and they've given orders an alias O. So when they do this from customers, next to it is the letter C, and orders next to it is the letter O. That's basically giving them aliases so that later on you don't have to type the entire table name. I am actually not a fan of this syntax. I think that the previous slide is really just as easy to type, and it's crystal clear what's going on. As soon as you start using aliases that are C's and O's and D's and Q's, I think it actually tends to obfuscate what you're trying to accomplish. But if this works better for you, that's totally fine. I'm not going to copy and paste this one. This will achieve the exact same goal as the previous query. It's just slightly different syntax using that alias notation. Instead of using the on clause, you can also use the where clause. This will still accomplish the exact same goal as the previous two queries. So in this case, we're still pulling the same information from the same two tables, from customers, comma, orders, where the customer ID in one table equals the customer ID in the other table. And in this case, they're sorting by order ID. So nothing new here, just slightly different syntax, and you can do it like this, or if you want to, you can use the where clause with alias. So you have 4 queries in a row in this slide deck that result in the exact same thing. They're just different ways of writing the SQL terminology to get this relationship to work. These relationships can be across more than 2 tables. So in this particular case, I'm going to assemble everything that I think would be necessary for an invoice for a specific order. There's an order number 11080. I want to know everything about it. So you went and looked at the actual raw data in your database. So I've got my CSI database, and I went and looked at my tables, and I looked at my orders tables, and I viewed my top 200 rows. We'll see that we have an order 11080. It was placed by this API. We've got customer information, order date, ship date, all that kind of stuff, right? So we got a bunch of information about the specific order. We then have information in the order details table, and that is associated with 11080. And you can see there are actually 2 different items that were ordered in that order, item 37 and item 42. And we've got some prices for those. We've got some quantities for those. We even have potential discounts. There's a discount of 10%. And then if we wanted to, we could go look up those items in the product table, right? We could look up 37 and 42. So I could open up that one and I could say, well, what was 37? 37 was a Douglas fir, and I can see some information about that. And 42 is this Fortune rhododendron. But rather than doing this manually, where I'm opening up all these tables and examining them myself, let's see if we can write a query that would combine all this information into a single place for us. So again, I'm going to copy and paste it, and then let's talk about what it actually does. Oop, can't do that. There we go. We're going to pick up the customer ID, the last name and the first name, and the address and the city and the region and the postal code, all that good stuff from the customer table. From the order table, we're going to pick up the order ID and the order date and the quantities and the product names. And from the product table, we're going to pick up product name and unit price. And if there are places where this information exists twice, you need to specify the table name. So customer ID appears in multiple places. I've got to specify that I'm going to pull it from the customer table, which has an alias of C. The order ID comes from multiple tables, so I'm going to specify that I'm going to pick it up from table O. And the unit price comes from multiple tables, and I'm going to specify that it's coming from table P. You can see that this is going to be coming from customer table, which has an alias of C, which I'm joining to the orders table, which has an alias O, which is joined based upon this customer ID equal customer ID. And then I'm joining that to my order details table, and they're joined based upon the order ID. And then I'm joining that to the products table, and I'm joining that based on the product ID. So there's a lot going on, right, in terms of all these different tables that are talking to one another, and how they talk to one another, and how they're related to one another. And then I finally have a criteria, which is I only want to do this for order number 11080. I can do it for every order. I can do it for a range of orders, but in this case, I'm doing it for a single order. If I do this and I run it, I think I must have pasted something wrong. Hold on a second. I had this working earlier. There we go. You can see all of the customer information, all of the order information, and all of the product information in one place. You can imagine this being your invoice that shows this is exactly what you're ordering for us for this order number. And then you can imagine then formatting it and saying, the order number goes up in the top right corner and the customer information goes in a block somewhere, and then the individual items go in the invoice body. So you could format this thing to look pretty, but this is the information you would need to actually create that invoice that you would eventually send to a customer. And you could do this for any order number you want. So this is kind of a cool way of combining multiple tables and showing all that information in a single place. And you could accomplish the same thing using this where statement instead of the join statement. So you can see very similar, just slightly different syntax where you have a where and, but this will give you the same result. So if I come over here and paste that one and try it, exact same results coming out, just slightly different syntax. You are welcome to use whatever syntax you feel is more comfortable. I'm never going to police that. So on an exam at the end of the semester, if you like the where statements and somebody else likes the join statements, totally fine with me. Whatever works, as long as you're getting the right results and you're using proper SQL syntax, I'm happy. So I'm never going to police which one is better or worse. There's no such thing. All right. So what we've demonstrated so far are inner joins where things are equal to one another. But sometimes the question we want to ask is not where they're equal, but where they're not equal. So an outer join is a join where the rows do not have matching values. But nonetheless, we're going to have some common columns that we're going to include in the table. So in the inner, I want you to think about it as like a Venn diagram where the two circles have some place that's going to cross. In the case of customers and orders, orders is completely contained by customers, right? An order can't exist unless the customer places that order. So that circle is completely contained by customers. Sometimes there's just going to be a small overlap where maybe there's some customers that have ordered certain products, and maybe there's some products that have been ordered, but not all products have been ordered and not all customers have placed orders. So there's not necessarily a complete overlap there. So there might be places where we just have some overlap, there might be places where we have complete overlap. And we might ask the question of where do we not have overlap? Where are there places where we don't have commonality? And that's kind of an interesting question. We might also say, I want to see where we do have commonality and where we don't. And in fact, that's one of the queries I'm about to show you is whether we have commonality or not, I want to see stuff. So this query is going to list the customer's information, their ID number and their name, and the order number for all customers. And that means that it's going to show customers even if they've never placed an order. So it's all customers. So if you look at the syntax, before I actually put it over into SQL, let's look at it. I'm selecting customer information and order information from the customer table and the order table. But in this case, I'm doing a left outer join. Left is the first table. It actually reads from left to right in English. And so the left table is the customers table. And that one is going to get included no matter what. We're going to see all the information from the customers table. We're going to include the order table when we can. If we can't, we're just going to show that it doesn't exist. So it will still allow this information to show up. So think about this. We've done this before where we showed only customers that had orders. We had an inner join earlier. But if we do this left outer join and paste this in, we see every single customer. The first bunch of customers are customers that have never placed an order. So I'm in there and I've never placed an order with this company. And same thing with Terry Adams and Martin Bankoff and Roland Hartano. There are a bunch of people in here that have never placed orders. So their order ID is there, but it lists as a no because they've never placed an order. And then we get to the customers that did place orders and we see the specific order numbers, right? So we can see that Ackerman placed this order 11080 And of course, again, customers might show up more than once if they place more than one order. So we can see all the people that have or haven't. We include all of them. Yeah. Now, and I haven't done this before. I hope this works. I hate when I do this on the fly, but we're going to try. Where orders dot order ID is equal to null. I'm not sure if that's going to work. I have the syntax is a little bit screwy here, so I'm not quite sure if this is going to work. It looks like it might yell at me, but I'm going to try. No, I didn't get it quite right. I have to go play around with this and see. Maybe it is null. But the idea here is, I'll fix this and I'll show it to you. That's what I get for trying to do something on the fly here. I'll fix it and I'll post something on eCampus. But you could do something where you only show this top group, which is customers that have never placed an order. And that one could be super useful, right? Like these customers came to our website, they gave us a bunch of information, and they've never bought anything before. Maybe we need to send them an email with a 10% off coupon. That's a very useful email to potentially drive some customers to make at least their first purchase with us. So I can't remember the exact syntax off the top of my head, but I'll come up with it and I'll share it with you guys after class today. That's an interesting one. So left outer join, we include everything from customer, whether they have a matching corresponding value in the order ID table or the order table or not. Okay, so very different than the inner join. Other things we can do, you can take multiple queries and you can combine their results. So this top query stands alone. It's going to pick up information from the customer table and the orders table. It's also going to create a column called min max, and in that it's going to put the word largest quantity. So I'm not going to do that. And we're going to match these two tables on customer ID. And the criteria is that the quantity is the maximum quantity from our order details table. Then I have a second query, select my same information. So you'll note that the select part of this is exactly the same in terms of the number of columns and the types of columns, the types of information. They match up, right? Each one has customer ID, each one has last name, each one has first name, each one has quantity, and each one has a column called min max. The top one puts in the word largest quantity. This bottom query puts in the word smallest quantity. They're the same as far as the columns of the table, because we're going to basically match these two tables together. So we're going to have the top table and the bottom table, and they're going to be matched together. Well, they have to have matching columns, so they actually parallel each other and match up. Okay, so all the columns match up. Beautiful. Slightly different criteria down here. This is where the quantity is going to be equal to the minimum from the order details. And then we're going to use this union between the two to have them both show up at the exact same time. This is really neat. Let's show what the result of this looks like. Here we've got all of the customer IDs, the last names, the first names, and the quantities. And you can see for most of them, we've got a whole bunch of smallest quantities. There are a bunch of ties for one, because they ordered one of those things. So there isn't a lot going on there. There's one person, Joe Barry, who's in there that has a quantity of 12, and so they have a largest quantity in there. So they have both their smallest amount they ordered, which was 1, and their largest amount that they ordered, which was 12. If there's anybody in there who had ordered more than quantity of 1, we would see multiple entries for them as well. So the end result here doesn't end up being that interesting, but the idea of matching these two things up and showing everybody's minimum amount and everybody's maximum amount, that's kind of cool. That's a neat way of doing that, using this idea of a union. So it's taking two queries that are similar in most ways with slightly different criteria, and then smashing them together. So you show them all as one big table. And that often is a really handy way of displaying your information. Okay. So the slides kind of talk through this. The union queries, the quantity and the data types of the attributes in the select clauses have to be identical. So you have matching columns in terms of what you're actually displaying. But other than that, the criteria can be different. Okay. Now, Every once in a while, we've got a situation where we've got tables that join to themselves. And so we've seen this in our modeling where we've done a relationship that's like a one-to-one or a one-to-many relationship with the table itself. When we write queries for that, it becomes really important that we are used to these aliases. So in this case, we're selecting the employee number from the E alias and the employee first name from the E alias, which we're going to rename employee, and the employee first name from the M alias, different alias, you know it's the same table, different alias, which we're going to rename manager. We're pulling from the employee table, E as an alias, and the employee table, same exact table, with a different alias, M. So we basically treat them as two separate tables that are looking exactly like they're basically clones of each other. And we say that the E.boss has to equal the M.employee number. Now, this is from the employee database, not the CSI database that I've been playing around with. And that caught me earlier today when I was practicing. So I got to make sure I come over here and open up a query for the employee database and try this. And here what you can see is that Alice works for themselves. Alice is also the manager for Ned. Ned is the manager for Andrew and Claire. Alice is the manager for Todd. Todd is the manager for Nancy. So it does this entire hierarchy, not by employee number, but by employee name, which again, if you were going to try to build out like who do you answer to, you probably don't want employee numbers, you want those names. So being able to write a query that displays this information like you're seeing right here is really, yeah, so this is a cool one. And again, in order for it to work well, you need these different aliases so the same table can be used twice and we can refer to which one we're using in one place and which one we're using in the other place.
I have a quick question.
Yeah.
Does this one work if someone didn't do the update query like they were supposed to initially? Like if you just typed it all in.
What's that?
You know how with that EMP database, if you didn't do the update query, it looks correct, but it really isn't. You have to do the update to say that there's that relationship.
So I think this will still work because this is still setting it temporarily as a SQL query, the relationship between boss and employee number. The relationship you're creating with that update query is enforcing that rule so you wouldn't be able to add data to the table where a boss didn't already exist in the database. But this one is saying, as long as you got data in there, you're an employee and you have a boss, we'll look where those two things are equal to each other and we'll pull that information back out. So if you didn't do that update query and you entered nonsense data, this might break. But as long as your data really is correct, this query should work whether you updated the data table or not. Should function.
Cool, thank you.
Good question. All right, so another thing that we can do in SQL is we can write subqueries. So basically a query within your query. This is where we get into either inception territory or was that Pimp My Ride on MTV, where he's going to put all kinds of crazy stuff inside your vehicle. You can put a query inside a query inside a query if you really need to, okay? And it can get really complicated really fast. You only do this when you need to, but sometimes you do need to actually ask a second question to answer the first question kind of as a whole. So we're going to look at a couple of different subquery examples. Again, these get complicated, and I'm only showing you a taste tester of these. We're definitely in territory. We're going out and Googling things and trying things out with these select queries is the name of the game. A select query is never affecting the data behind the scenes. It's merely showing aspects of the data to you on the screen. So you can't do any damage. You can try out as many select queries as you want without doing any damage or any harm to your database whatsoever. So try this stuff out until you get the result that you're looking for. Experimentation is absolutely the name of the game for this part of the course. So we're going to try a couple of these. Here's an example where we're going to pick up the last name and the first name from the customer's table, where the customer ID is going to be picked up from the orders table, but we're only going to pick them up as a distinct entry in the orders table. So this subquery is in this parentheses section down here at the bottom. That needs to already exist, right? So this is a list that's going to be used as the criteria for my where statement for the bigger query. So I'm going to go through my orders table, and I'm going to look at all the customer IDs, and I'm going to come up with a unique list of them. So if a customer shows up in there twice or 3 times or 4 times, I'm only going to basically record them as once. And I'm going to list of all the unique customers in my orders table. And then based upon that unique list, I'm going to show you everyone's last name and first name. If you don't do it this way, if you just pick up the last name and first name from the customers table, where the customer ID equals the customer ID in the orders table, you'll get customers repeating a bunch of times. You probably even tried this if you've experimented at all, and you get something that it's right, but it's very repetitive. So this is a way of getting this repetition eliminated, is only show the customers based upon them only showing up once in the orders table. Let's try this one out. And again, make sure I'm going back over to my CSI database and writing it here. Each person is only going to show up a maximum of 1 time. And this list is only the customers who have placed orders. So I'm not in here because I've never placed an order, even though I am a customer in the customer table. I don't show up, and each customer in this list only shows up 1 time. Super duper useful query that is a good example of a subquery structure. Okay, so this one is one worth paying attention to for sure. Now, some subqueries are correlated and some queries are uncorrelated. Uncorrelated means you don't depend on any of the data from the outer query in order to run the inner query. The inner query could basically stand on its own and run. So that means that that inner subquery can basically be run once, you get a result, and then you use it to inform the outer query, and you run that one once and you get all your results. And that's exactly what we had this past time. This one, I really only need to run that inner query 1 time. I'm going to get the result. It's not dependent on anything about the last name and the first name. It's just give me a distinct list of customer IDs in the orders table. Once I've run that 1 time, I can then run the outer query and say, based upon that list, match up on that list and tell me last name and first name. Sometimes you have correlated subqueries where they make use of data from the outer query. They basically are informed by the outer query for the inner query. And that means that they are executed every single time you run the outer query. So you have to basically run each one twice. And they can use the exists operator, but it's not necessarily required. So this gets to be kind of complicated. Let's see how this might actually work. In this case, we're going to select a distinct order ID from our order details table where exists, and then we have this subquery. Select everything from the products table where the product ID is equal to the product ID from the order details table, and the category ID is equal to 3. So this is a correlated subquery. It always refers to an attribute from a table referenced in the outer query. So it's referencing some of the information on the outside, the order ID from the order details table, and it's picking up each distinct one. And for each distinct one, we then go and say, hey, go see if this is true and find out if it's true or not. And then when that exists, then we would display that outer information. So it's informed by the outside. The subquery is testing for a value that comes from the outer table. What does this actually do? Hold on. I didn't paste correctly, sorry. These are orders from the order details table where the category ID is equal to 3 that are, and just distinct ones that are in the order details table. So if the category ID was equal to 3 in the order details table, we're going to show uniquely each of the orders that match up with that. You can see this 11, 111110, 11122, and we can certainly go look at the raw data and see if that makes sense to us. If I go look at my top 200 rows here and go find that 111110 here, we've got these guys, right? And so we got a bunch of different entries in here for this 111110, there are a bunch of them. And then we could go look at the orders table as well at the top 200. And we've got these 111110, this one, right? So we've got all this information and we can see if that actually makes sense where it all matches up. So our orders table and our order details table, we're basically getting this result where the category ID has to be equal to 3. And I have to even go look at the product ID. I haven't gotten there yet. So I look at the orders table and I look at the order details. And if I look at the order details, I've then got to go look at the products that match up. And I would have to verify it. It would take a little bit of time here because we got a bunch of different products, right? But if I look at all the products that are part of this thing, one of those products in the products table, let's go look at the top 200 rows, is in category 3. Do you want to do that manually? I don't. I could. It is extremely tedious. And think about how quickly I was able to just click execute here and get, these are the 5 products where we have them in the order details. So we ordered those products, they're part of an existing order, and they're in category 3. You wouldn't be able to do it simply manually in any way. It would be really cumbersome. Okay. Let's look at a derived table example. This one's complicated. This shows all the products where the standard price is higher than the average price. So we have to figure out what the average price is across the entire table. And then we're going to have to check to see if the price that we are looking at for an individual product is higher than that average price. So inside our outside query, we've got this subquery, select the average unit price, which we're going to give a nickname, AVG price. And this column of the subquery is an aggregate function, right? So it comes up with just a single number for each of the, or for the entire table, just one number. It's 19. I think it's like 18 something. We're going to see in just a second. Comes up with a single number. I give it an alias, AVG price, and I give the result of this query an alias. You have to give an alias for the derived table, even if you never use it. And I don't know why, but this is true. This thing won't run unless you give this table an alias. And certainly you could refer to average price as X dot AVG price up here. That will work, but you don't need to. And then the criteria is based upon the result of that inner subquery, right? I figure out this average price, and now we're checking each individual unit price and saying, only display a product if its unit price is greater than that average price we came up with. So let's look at the result, and it will make common sense, but how you actually write this as a query is a little tough that first time. So in this case, you can see I'm showing you a magic lily. Its unit price is $44. The average price across all products is $17.98. Is $44 greater than that? Yes, magic lily gets to be shown on this screen. And if you look up and down these prices, you won't see anything that's not greater than 17.98. The closest here is $18. I don't see anything else that's closer. Here's an $18.95. There are products that have unit prices that are lower than that. They're not included on this list. These are only products that are above average cost, right? The price is higher than whatever our average price is. So again, does this make sense that you might actually want to know this? Let's see all the products that are slightly more expensive. Sure. How do you actually come up with that query? Well, here's an example, so you could base your future queries on this example and come up with a similar kind of result. But first time around, that's pretty challenging for sure. So I am only giving you a couple of examples of this. You can find all sorts of examples of subqueries, inner joins, outer joins, left joins, right joins, all that kind of stuff by Googling. You guys absolutely have the ability to do this and try some of the stuff out, like I said, and then experiment. And there are a whole bunch of problems I'm giving you in the workbook that I would like you to work through to experiment. You do need to be familiar with the data model and how the various relationships work. So how our entities are linked to one another, because often The foreign key, primary key relationship is what you're going to want to use for joins. It's pretty rare that you would want to create a join that isn't already enforced. It happens, but it's not very common. So if you're comfortable with the structure of the database to begin with, then you'll be more comfortable with where you should probably start with some of your join queries. You obviously need to know what your final results should in general look like. And that is where, again, I was kind of hinting at, well, that category 3 query, I probably want to at least check one of those orders all the way through and say, okay, this order showed up. I've got these 8 different products. I'm going to cross list these 8 different products in the products table. Aha, there's one that's in category 3. This thing worked. I'd probably do like a spot check once or twice and make sure that what the query is giving me is what I'm imagining is going to happen as well, right? So you're going to be comfortable with what you think your results actually should be and what kind of attributes you want to report in the results. I might suggest to you that in this query, displaying the average price may not be necessary, right? If you're going to just suggest that this is a list of all of our high-priced products, repeating average price over and over and over and over and over again is probably not all that useful. So you may want to just leave it out. I might not need to show it, even though it's part of the calculation. It's critical to how the query works. Displaying that number 30 times or 50 times, maybe not so much. Right? So it's important that you know what you want to actually have show up on the screen. Sorry, my mouse is fighting me. Hold on a second. You're going to want to identify any entities that do have those attributes and then figure out how they actually work. Maybe you need to even go back to your ERD and sort of review that visual diagram and understand where things are actually going. You are welcome to use either join clauses or where clauses anywhere you have a link. I don't care what syntax you use. You're going to want to probably be consistent, but maybe one makes more sense to you when you're looking at it than another, and that's totally fine. No problem with that. You're going to want to potentially play around with group bys or havings. That's kind of the other earlier chapter, but you could certainly come back to that with some of these more complicated queries and get some interesting stuff out of your advanced queries as a consequence. And you might have to think about unusual data. You might have some situations where you just have some weird stuff going on in your database. It's accurate, but it's strange. And that might affect how your queries work. And you might have to write some additional clauses to filter out some strange stuff or change some stuff. I don't know, right? But this is definitely worth considering as you move through these types of questions. For efficiency, which is not a major concern for us in this class because we've been dealing with small databases, but might be a concern for you as you're working through your visualization projects, depending on how big your data sets are, and absolutely is a major concern for real organizations that are dealing with humongous databases, tons and tons and tons of data. You want to think about how efficient the query is, how well it works. Instead of doing like a select star, selecting individual columns, only the columns you really truly want to see will allow the query to run faster, especially in a situation where you might be in a network environment, you're reducing the amount of network traffic for the result set that's getting returned to you. So if you know you only need to see one column or two columns, do that instead of doing a select star, which can be overkill. Again, for our purposes, these little bitty databases we're playing around with, that shouldn't matter very much. But in the real world, it certainly does matter. Subqueries are computationally expensive, especially if they are a subquery that is one of the ones where you're deriving it, or not deriving, where you are, I'm getting the terminology mixed up. The subquery is requiring that result from the outer query. Correlated, that was the word I couldn't bring to mind. Correlated subqueries are really computationally expensive because this inside query has to run over and over and over again for every distinct result you got on the outside. So computationally, that's expensive. If you can avoid doing it that way, you should. Sometimes that is an easy way of getting some result, but if you could actually write a query that doesn't require that, it's probably better. And if your data is going to be used lots and lots and lots of times, what you might eventually do is create a separate query and store that result, even if it's a temporary table, push that information out to a temporary table so it's stored, and then ask questions of that query anytime you need it. So one time you saw me create a sub table in one of my databases for everybody who is in Texas. If you really did only care about Texas customers regularly, so maybe I'm running a store in Texas and the only thing I care about are my Texas customers. Well, then before I do any work in the database for myself, I might create a query that creates a subtable, which is these are only the Texas customers. And then I don't have to look at the entire data set. I can only look at the data set that's relevant to me. And that allows the processing to work much, much faster, right? So you basically shrunk the data set down by an enormous amount sometimes, and then only look at the data that's relevant to you. And you haven't affected the rest of the data. You're just only looking at a snapshot of that data. That does mean you need to synchronize those snapshots at least occasionally. But if it's something I'm doing that's historical data from a long time ago, that might not matter very much. That might not be all that difficult to do. So if you can and need to, creating separate queries and storing the results might be a more efficient way of handling things. Other guidelines for better query design: indices can be used in query processing. All primary keys are automatically indexed, but you can add additional indexes if there are specific attributes that you're using regularly as query constraints. So if there's some sort of criteria for a query, you might want to index them to make the query run a little bit faster. That does mean you're storing a little bit more metadata in your database about specific attributes so that they are being stored and indexed accordingly. For bigger databases, optimizer statistics are relevant. Not relevant for us, but there are things you can do to optimize your database, and you can check it and see if it's running as well as it possibly can. Using compatible data types, right, for various fields so they talk to one another, or literals so they talk to one another a little bit better. Keeping your queries as simple as possible. If they are complex queries, maybe even breaking them out into simpler parts and doing a long-term storage might be a better bet. Putting one query inside another query is computationally expensive. If you can avoid it, you should. Doesn't mean that always you can, but if you can avoid a query within a query, that's not always the best way to do things. We can try to get away from that. And definitely don't combine a query with itself. So things like self joins are typically bad news. Sometimes that's required. That's how the data is really structured. There's nothing we can do about it, but if you can avoid it in some way, that's probably a good thing. So queries that are referring to themselves can sometimes be a mess as far as the calculations are concerned. A lot of these last couple slides, by the way, I'm trying to emphasize, not really relevant to most of what we're doing in this class. But if you ever are talking to some database administrators at medium to large scale organizations, this is what they are dealing with every day is, we can get any information you want out of this thing, but can we get it to you in a timely fashion without bogging down the entire network or bogging down our database servers? And we want to be able to deliver this information to customers rapidly. We're not even talking about how relational databases really don't work when we get to big databases and how we have to move to completely different systems. We don't even talk about big databases in this class. They're a completely different beast. I don't even know that much about them, honestly. I just know they're really different. We're well beyond that. We are only talking about pretty simplistic databases. So a lot of this concern about efficiency is not all that big a deal. I already talked about creating temporary tables and trying to parse things out. If you're only looking at subsets of the data, you may need to combine update operations. Update operations, again, can be computationally expensive. Only go get the data you need and use that locally. Don't get the entire thing. Don't ask your database to sort if it doesn't already have an index. It can take a huge amount of time. So all kind of general lessons that we should be following when we're working through databases to try to keep things working efficiently. But for any of our examples, probably overkill as far as what we're trying to do. So just a taste tester on some of the more advanced techniques that you can use for queries. What you're going to want to do to really understand this stuff is not listen to me. What you're going to want to do is work through it. So if you go and look at the SQL workbook, and I'm pulling up right now, we already worked through a bunch of the questions in the SQL workbook, but we know there were a bunch we didn't get to. So if we get down here to the advanced queries, which starts here after the very last employee database. These are the ones I want you to work through that we are going to talk about together in class in a couple weeks. You have plenty of time, but I want you to work through them as if they were another homework assignment and get that submitted on eCampus. I'll put up a slot for it on eCampus and you can submit that. We'll take a look at it. And then I'm going to do the whole cold call in class where we'll work through all these different questions and you can try to answer these. And I'm going to encourage you to do your best to try to answer these things by yourself and not be tapping the smart person in your group and say, hey, how did you answer this question? You know, fight through it and try to push through some of these and try different things out until you can get a reasonable result. In a lot of cases, you as a common sense human being know what the results should be. So things like report the total donations in 2014 by state. You could look at that database and you can say, this is what this thing should be. For this state, the total donations should be this amount of money. And then you can try to write the query to give you that result, and you can compare and contrast and make sure that it's matching up. So the databases aren't that big. Being able to have sort of a check value is available to you. So I strongly encourage you to do that. And so you just have a couple pages of these advanced queries that I want you to try to work through. And then we'll meet up in a couple weeks and we'll talk about it. Okay. Any questions for me on the next step in query language? We're good? And we're good on our schedule. So I won't see you this Thursday, but next Tuesday, I'm going to see everyone and we're going to talk about your next stage in the group projects. Yeah. Okay. I'm going to stop recording. Thank you, everyone.